everyone. Thank you for joining us today. My name is Grigorii Alekseenko, and I'm here to talk about our recent paper. It's called Beyond Specialization, Assessing the Capabilities of MLLMs in Age and Gender Estimation. It's presented to you by Layer team at the R&D department in Salute Devices. And firstly, I'm going to introduce our team to you so you can understand about what we really know about this topic. Our team is an experienced machine learning team. We have really big experience and some state-of-the-art results in topics like AI-generated text detection, moment retrieval and highlight detection in video, age and gender recognition in terms of images, and multimodal models and more, but we'll stop here. Authors of this paper are Kuprashevich Maksim, is the leader of Layer team, and myself, Alekseenko Grigorii, and Tolstykh Irina are senior researchers in Layer team. Firstly, we need to talk about some related works. This paper we are talking about is highly dependent on other work. It's called MLLM, multi-input transformer for age and gender estimation. It is done by Maksim, Kuprashevich, and Irina Tolstykh, and there are some achievements made by this paper, like state-of-the-art performance on a couple of, or better to say, a lot of data sets. This paper is a precedent to our current work. The problem of the task of age and gender recognition is that we need to understand what type of person do we see at the picture. For example, for better recommendations, like in terms of goods recommendation in marketing, like in our initial case, but there are some other ways to use this network. For example, for safety, for person verification, and there are a lot of many other ways to use it. We're going to look at specialized models like MLLM itself. Then we're going to discuss something about MLLMs models, or they called VLMs. We're going to compare them on age and gender recognition task. And we're going to discuss pros and cons for using some of the models, and let's dive in. Firstly, specialized models. In this case, we mean this is usually small models that are very fast to inference. They are used for specific tasks. There are not foundation models. They are not generalist models. They only can do one specific task, or maybe a couple, but they should be closely connected. And they may be run on a local machine or a consumer level GPU, because in contrary to today's big language, large language models, it's likely to impossible to run them on consumer level machines, and it makes them unreachable for a broad person beings. Um, this this is another predecessor to Mivolo paper. We're going to do a little recap for this evolution, and it's based on Vision Outlooker for visual recognition. Basically, this is a model that combines um, mm, that combines attention using, like in transformers, for example, visual transformer, and convolutional methods. So this is kind of hybrid architecture that makes it a little bit better in terms of inference time, in terms of data that we need to train it, and in terms of training speed. Mivola first model was an improvement to this Volo model, and here at the slide you can see overall architecture. It is used multi input, as it's said in name of model. Multi input means that we use face crop and body crop to get as much information from the picture as we can. Then features from face and body passed into feature enhancer model that makes fused representation, and then we get to standard Volo architecture, and as an output we use gender and age simultaneously with two heads separate for each type of output. A little bit deeper to the feature enhancer model. It uses cross attention to merge face with body features, and this is a double cross attention between face and body, and then between body and face, with switching them in places. And in the end, we get fused joint representation, so we can use it as one, where features of face complete features of body, and vice versa. In this paper, we produce you Mivola second version. It has better resolution, so it's trained on 384 pixels resolution. There are some other key features that are survivors of any tries to improve it, and face blur got us a little bit better two-stage training, and dataset extending with another 40% of initial dataset. So let's move in and see a little bit closer. So about face blur, it is used with a 5% chance at the stage 1. Stage 1 includes only training one input with only face crop. There is random replace with empty tensor that is going to be on stage 2. In stage 1, this has no meaning because then it will be no input information. After this net trained with stage 1, we are going next to stage 2. And then we can see that we added body crop and feature enhancer to the training process with extended input resolution and improved chance of face blur. It's about 70%. And there are replacing crop with empty tensor, so it's kind of a dropout feature for training. Sorry. Next, we're going to move to MLLMs models, and there is a little recap about what are they and how do we use them. MLLMs in general, or VLMs, means visual language models. It's models that combine big language models with capability of understanding an image. Usually it's made of backbone like large model with, for example, vision encoder like clip model and some projection to tokens representation from language model. So model gets as an input an image and language instruction or language prompt. For example, asking what is in the picture, and the model gets to answer it properly. There are some key models that we used in our paper. First of all, it's LLaVA, presented by Haotian Liu, and it's based on Vicuna model or Llama model. There are some variations, and as vision encoder, they use clip VIT, large one, and multi-layer perceptron as a connector from vision to language. This is a good model. We used versions 1.5 and 1.6, and we are going to discuss them a little bit later. And also another model that we used, it's called ChatGPT 4V. And you can see at the picture, there are metrics of this model. It's highly based on LLaVA architecture, but there are some big work with data for training, and this model outperformed LLaVA 1.5 and other models. So we thought it is a really good model to try. And at the moment of our research, this model was brand new. We tried to fine-tune models. We compare at the end models like vanilla, like they trained from others, and then fine-tuned on our data set. We present here hyperparameters for our fine-tuning, and we trained it on 8 A6000 NVIDIA GPUs. These parameters are like really common, and they do not share something specific. Uh, it means that these models are easy to train, and there are no like special tricks to train them, and it can be done by a lot of persons. They need just to just to move along with README and um, obey it very well. Some metrics that we use in our paper: mean absolute error and cumulative score for age estimation. Age estimation is done in terms of regression task, and gender prediction is done in terms of binary classification task. Additionally, we use mean average percentage error with factor of 1 um, to avoid dividing by 0, and this means like around a year error that we allow models to do an error. There is a table with results of comparisons of fine-tuned models. So for these models, there are only one image input available because of the way they were trained initially by their authors. And we used body crop, and we tried to compare it with face crop on ChatGPT model, and it shows that VLM's models use body crop more successful than face, and so we move on to using body crop in next comparisons, and the best models are shown, like it's ShareGPT for V with 7 billion parameters, trained just a little than half of epoch, and it shows the best mean average error, cumulative score, and good performance in gender, but not the superior performance in this comparison is by 13 billion parameter model. You can see that models that use body crop are really good at predicting gender. Just yeah, there is not much to 100% accuracy. And we also compare our models to ChatGPT 4V, and then we added later comparison with ChatGPT 4o. Here we share the prompt we used to it for all the MLLMs in fine-tuning, in using vanilla model and using ChatGPT model. We can't tell much of using ChatGPT. I mean, because it's closed model and we do not know what architecture precisely inside. We trained our models on Legenda dataset. It is presented in the first paper, Mivola, and in this paper there is a little bit increment improvement. We added 40% more of training data. It's highly annotated, so it has really good quality, and there is a benchmark that created by human annotators on crowd platforms like Mechanical Turk and others. There are some data sets that we need to talk about more. There is a Nano Legenda data set. Basically, this is a subset of Legenda data set. We had to use a random small subset and balanced it because of ChatGPT initially when it was released had a limit about of 100 requests per day, so we cannot use this for the whole data set. We had 200 random samples for each group of 5 years, and then we had to filter it a little bit more for because of ChatGPT refused to provide answers about age and gender of individuals at the photo because of safety reasons for models. And there is another data set. It's called Wild 104. We manually scrapped it and annotated from social networks. Unluckily, we cannot share it because we do not own these photos, but it is really challenging samples. And we use it to compare performance like in the wild. There is a table with results on Nano Legenda benchmark for all the models that we used. There are some vanilla models. They are the first 3 models, then closed models like ChatGPT, then specialized model like Mivolo, and fine-tuned VLM models on this task on this data set. As you can see, ChatGPT 4o has superior performance in terms of gender recognition, in terms of age recognition, but in gender recognition there are some problems. Mostly we think this is about safety reasons and about if we do not use closed models, if we compare open sourced VLMs or fine-tuned or Mivolo specialized model, there we can see that Mivolo performance is really good, but performance of fine-tuned ChatGPT model is a little bit higher. Then comparison on full Legenda dataset. We train here on Legenda dataset and compare on IMDb Clean and Legenda. We can see that Mivolo is better in IMDb dataset. ChatGPT is better on Legenda. And about Wild 104 benchmark, ChatGPT 4o model gives a superior performance, while between open models, ChatGPT shows really good results, and Mivolo also holds the best specialized model place. There are result metrics on this task. And on these graphs, it's divided by age groups. As you can see, the more age of individual in the photo, ground truth, the more models tend to do an error in absolute meaning. This is expected because of biological meanings, and we should use MAPI, as we said in the start, as percentage, or not absolute error, but relative. So at the end, MLLMs, um, without fine-tuning, despite they are not explicitly trained for analysis, they deduce personal attributes well, without additional training. And with fine-tuning, they do a really good job on determining person's gender and age. Specialized model like Mivolo version 2 surpasses generalist models in age estimation in terms without fine-tuning. GPT-4o is most precise VLM between which we compared. So it was at the time of GPT-4o release. And that's it for our paper. So there are some useful links to the sources of our of our work, and feel free to um, use these links, and feel free to ask questions if you do. Thank you for attention.